Well, thanks for joining me. We're going to continue our discussion and do a little bit of review of how to figure average atomic mass. And at the end of this video, there'll be a short little practice quiz that you can take to check your understanding. So let's begin. I think you know that atomic mass can have several different units, right? When we talk about mass, let's pick an example like oxygen. So if I said, how heavy is an atom of oxygen? Well, it's not very heavy, right? We know that. And what unit would you use? Would you measure it in kilograms or grams or atomic mass units maybe? Let's delve into this a little bit more. Now, there are, first of all, different kinds of oxygen atoms. What do I mean by that? Well, specifically, we could be dealing with isotopes. In our earlier discussion, like easy to say, right? We said that an isotope is the same element but with different number of neutrons. So I could have an oxygen that has a mass of 16 or an oxygen with a mass of 18. Okay? In molar mass, the unit would be 16 grams per mole, but in atomic mass, it would be 16 AMU. I could also be dealing with, just so that we understand, we have an atom, that's just O, but an ion is O with a 2 negative charge. And so an atom and an ion are very different. And even when we get to the atom, we have to specify which isotope we're talking about. And finally, we have allotropes. Allotropes are different forms of the element in the same physical state. So oxygen, when found in nature, is a molecule. There's O2, like the oxygen we breathe, and there's O3, ozone. Okay? So these are all important terms for you to know. Allotrope, isotope, atom, ion, molecule, and you should be clear on the difference between each of those. When we talk about what an atom of oxygen weighs, we're generally talking about its average atomic mass. So if we stick with oxygen for a moment, oxygen has, well, I'm going to tell you, at least for this point, it has 3 isotopes. There's oxygen 16, and that's the majority of all the oxygen you find. There's oxygen 17, a very small, very, very small percentage, and oxygen 18. Now, if you remember from yesterday, we said you can calculate average atomic mass. Average atomic mass is equal to the mass of isotope A times its percent abundance, plus the mass of isotope B times its percent abundance. Notice when I do percent abundance, I multiply by the decimal percent. So 99% would become 0.99. And then finally, I have to add, looks like a little typo here. This should be 18 AMU, because this weighs 18, times 0.002. I'm pretty sure when I did my calculation, I did it correctly though. So if you were to add up those 3 portions, you would get a number, 16.00238. Now, let me move myself out of the way for just a second. Oh, I'll put myself up here. All right. Here's the block from the periodic table. It says 15.9994, yet we got 16.00238. Again, we're looking at different isotopes, right? Depending on, are we using all these or maybe just the main ones that are more common? So it turns out if I were to only use oxygen 16 and oxygen 18 in my calculation, it ignored oxygen 17, I would have got an average atomic mass of 15.99592. Pretty close to the number we're seeing over here. Okay? All right. So when you calculate a number on the periodic table, it's based on the natural occurring abundance of each element. If they're radioactive, if they're unstable, oftentimes we get rid of those and don't even include them in our calculations. So in general, if I say how much does an atom weigh, I'm not interested in grams because it'd be way too small. Instead, what unit would I use? Atomic mass unit, or AMU. You got it. All right, let's keep moving. Now, I mentioned on the earlier video that when you're looking at an AMU, you need to know, well, how big is that? Well, if you were to take the mass of a carbon-12 atom And so this represents the mass of a carbon-12 atom here. And divide it by 12. So 1/12 of that carbon-12 atom, that mass is equivalent to 1 AMU. Each isotope then has its own atomic mass, right? Oxygen 16 weighs 16, oxygen 17 weighs 17, and so on. And what we need to do is average them from their percent abundance when calculating an atomic mass to put on the periodic table. So let's look at some of this here. I've got a bunch of percentages of isotopes of some elements here. And so hydrogen, for example, has, well, I'm showing two isotopes, H1 and H2, with their percentages. Now, the fact that this is 99.98% of all hydrogen, the average of these two is going to come out really close to 1. And when we look over here for hydrogen, it's 1.008, as we might expect. Looking at carbon, it's about 99% of it weighs 12, and 1% weighs 13. Again, if you average that, it's going to be very close to 12, just a little bit over that. And if we look, carbon 12.011. Nitrogen, again, the vast majority weighs 14, a little bit weighs 15, so we would expect it to be just slightly bigger than 14. Here we look at nitrogen, average mass 14.007. And you could go through all of these if you wish. I'm not necessarily going to go through each of those for you. Let's focus on maybe this one down. Well, let's do this one here. Bromine, it's roughly a 50-50, isn't it? But it's 79 and 81. Well, what's halfway between 79 and 81? 80. And look at the mass of that bromine, 79.904. It's going to be favoring slightly below the 80 because the 79, the smaller of the two masses, is slightly bigger. All right. So if we were to take methane, now methane has a chemical formula. It's natural gas, CH4. It says for carbon 1 in 90 carbon atoms are carbon 13, and the rest are all carbon 12. So that means carbon 12 is 98.9% of all the carbon you find. So for approximately 90 methane molecules, only one of those would be carbon 13. So here's a visual representation of that. I've got my CH4, the little green circle is carbon, the yellow ones represent the 4 hydrogens. So each of these is a methane molecule. And if you count them, there should be 90 of them there. And notice this one, the carbon's a little bit different, okay? Because this one is a different isotope of carbon than all the other ones. So it's kind of like Where's Waldo, right? Find the missing little character. So he's right there. There it is. Right? That's carbon 13, and all the rest are carbon 14. Using a letter with a hyphen and a number is called isotope notation. This number represents the mass. We know that all carbon has 6 protons. That's what makes it carbon. So we wouldn't write ever, C-6 unless there was a carbon that had no neutrons. Then it would weigh 6, but that doesn't exist. All right, I'm going to skip this one on the rocks for right now. Let's go here next, okay? So I've used these terms before, but I didn't define them properly. I want to give you a small little mnemonic to help you remember them. So an ion is a little bit different than an atom. An atom is neutral. An ion has a charge. And there's 2 flavors of ions. They're either cations or anions. So an ion is a charged particle. Now, you might think that an anion gets a negative charge if it gains an electron, and you would be correct. You might also think that a cation becomes positive when it gains a proton, and you would not be correct. Protons are never gained or lost, only electrons. So how can we get a positive charge? Well, if an atom loses electrons, it will have relatively more positive charge. So that's what happens. So a cation is a positively charged ion. See, when you write cation, depending on if you write it in uppercase or lowercase, if you write a lowercase t, it starts to look like a plus sign, doesn't it? And if that helps you remember that cations have a plus on them, great, and use it. I'll give you another way to remember it, right? Maybe you like cats. Cats got those really weird eyes. Now, I had a bad experience as a child. My cat ran away from me when I was moving, and it scratched me, and I was left crying. And so I don't really like cats that much. So, you know, this one's on me. So if I offend you on this one, I apologize. I'm simply trying to help you remember, excuse me, cations are positive. So if you look at the cat eyes, they're kind of weird. Their pupils go up and down when they're alive. When they're dead, they might look more like this. So now you see how those are plus signs, right? Or maybe they're just X's because the cat's dead. And if that makes me happy, that's a positive. Anyway, that's a warped way to think about it. Let me give you another way. Cations form when metals lose electrons. Generically, I'm going to call a metal M. It's going to lose an electron with a negative charge, leaving it with a plus charge. If I have a metal and it loses 2 electrons, it will have a 2 plus charge. The last way I remember this is sometimes I ask students in class, what type of music do you like to listen to? And people will say contemporary or hard rock or country or, you know, I like Motown music. And there's always one kid that says, I like heavy metal. And I'm like, man, you must be a loser, right? Now, I'm really not insulting them. I'm not trying to. Here's what I'm trying to get you to think about. Metals are losers. Forget that people that listen to heavy metal are losers. That's not what I mean. What I mean is metals lose electrons, okay? So metals are losers. If you lose electrons, you end up with a positive charge. All right, an anion, look, if you break that down, it says the N here, negative ion, a negative ion, anion, right? If that helps you remember it. Here's another way, right? There's this guy, Justin Wilson. He's called the Cajun Cook. He used to be on TV, and he would cook. First of all, he would wear, like, he's from Louisiana or something. He'd be out in the bayou somewhere in the middle of the day, and he'd have his bib overalls on and no shirt. And they had to put subtitles on him, even though he was speaking English. And he would say, like, I'm gonna cut off some onion with some crawdad. Right? He's saying onion and crawdad, but it's not like onion. Now, I put a couple little videos here of you just to hear. Now, how does this help us? Well, look, when he says onion, it sounds like onion, onion, right? Or if you think about, if you cut an onion, it makes you kind of cry, doesn't it? You tear up, and that's a negative. Nobody wants to be cutting onions and crying, right? I'm going to play for you a little bit of Justin Wilson so you can hear his wonderful Cajun accent.
But I got a story I want to tell you. There was a city-speaking friend with me what went hunting for squirrel year before that. He went in the swamp down near where I live. In his heart, too early to hunt them squirrels now. I'll kill them squirrels. He said, look, son, I ain't no game warden. Don't you got a pistol in your hand? He said, you got it hid in the swamp? He said, no.
All right, now you got a little bit of Justin Wilson. I put a couple of his videos on here. I think the second one, he's actually cutting up some onions in there. So, an anion, negatively charged ion, formed from nonmetals gaining electrons. Metals are losers, nonmetals are gainers of electrons. So, a nonmetal will want to gain electrons and form a negative charge. A nonmetal gains 3 electrons, it'll have a negative 3 charge. All right. Our next unit after this one will deal with, well, after we finish nuclear, we'll deal with the periodic table. And we'll learn that Dmitry Mendeleev, this guy that looks a lot like Hagrid from Harry Potter, he's Russian, he came up with the first modern periodic table that we would recognize as a periodic table. And his core belief was that he argued the elements' properties are functions of their atomic weights. Now, that's not what we believe today. Nowadays, we think that the elements' properties are functions of their atomic numbers. Now, atomic numbers are number of protons. Weights are protons plus neutrons. He wasn't completely wrong, but he also was not completely right. We'll discuss Mendeleev and how the periodic table is organized in much greater detail in the periodic table unit. All right, let's deal with trying to calculate an average atomic mass. So magnesium is an element. It used to be used if you had an old camera that had a flash bulb. That flash bulb had magnesium ribbon in it, and when it burned very bright for a quick second, right? The military uses magnesium flares. If you're in a fighter jet and in a dogfight, if someone's chasing you in the aircraft and they lock on you, you got just a split second to hit that little button, and it sends out the back of your aircraft magnesium flares that burn very bright and are actually distracting to the laser-guided missile because it's so bright it's kind of like flash blinded, and it doesn't know where you are, and that might save your life. Anyway, magnesium has three isotopes. There's magnesium-24 that's composed of 78.99% of all magnesium, and it has an actual mass of 23.985 AMU, but I'm going to call it magnesium-24. There's magnesium-25 that has this mass here, and it composes 10% of magnesium, and the rest of it is magnesium-26 with this mass. So I want to find what is the atomic mass of magnesium. So sometimes I like to make a data table, something like this, and perhaps that's what you'll want to do also. So I got my three isotopes, magnesium-24, 25, and 26. I don't want to write the abbreviated mass, 24, 25, 26. I want to use the masses they've given me so I get a more precise average. Now, I was given two of the percentages, but not the third. Now, you're sophisticated enough. You know that the three of these better add up to 100%. So right now, when I add these up, that's 88.99. So that means the rest must be 11.01. So even though this wasn't given, you should be able to figure that out. Now, to figure the average mass, average atomic mass, I take the percent abundance as a decimal, 0.7899, times the mass. And I'm going to write that over here. So I took 0.7899 times 23.9850, put it here. Well, what's 10% of 24.9585? You can probably do that one in your head. 2.49585. 11.01% of 25.9826 is this number. Now, if you were to add those three numbers up, you get 24.304 AMU. That would be the number that you would write on the periodic table if you were solving it. And if you have a periodic table in front of you, you look up the average mass of magnesium. It'll probably say 24.305 AMU, but that's pretty darn close. And now you know where that's coming from. Now, what is the chance that you could ever find an atom of magnesium that weighs 24.304 AMU? Well, the answer is 0. Okay? It's not like finding a four-leaf clover where it's possible. It's not possible. Magnesium either weighs this much, or this much. There are none that weigh this much. Yet that's the number we put on the periodic table. It says, if not told otherwise, the mass of the isotope is the mass number in AMU. Okay? If you're asked for a molar mass later on, that'll be in grams. But for right now, if you're asked for a mass number of an atom, let's go ahead and keep it in AMUs. All right, let's try another one. And then after this one, I'll give you a practice problem. So it says, calculate the atomic mass of copper if copper has two isotopes. 69.1% has a mass of 62.93, and the rest has a mass of 64.93. Now, feel free to pause the video right now if you want to try to work it on your own, and then come back and watch, and we'll go through it together. The first thing I did is I made a data table. I have my two isotopes, copper 63 and 65. I call this one 63 because it looks pretty close to 63. I'm calling this one 65. and I put those actual masses in. If this one is 69%, and I know the two have to add up to 100, then this one must be 30.9%. Now I've done most of the hard work. I just have to take my calculator out. If I take 69.1% of this number, so 62.93 times 0.691 gets me my 43.48463. Now I'm going to do the same thing down here. I'm going to take this number, 64.93, and multiply by the decimal 0.309, or 30.9%. And I'm going to get 20.06337. Now, what I'm really doing is using this formula down here. Average atomic mass is equal to percent of isotope A, 0.691, times the mass, 62.93, plus the percent of B, 0.309, or 30.9%, times the mass, 64.93. And then you add them up, and you get 63.548. And if it were my periodic table, this is what I'd put on it, as an atomic number of 29 and a mass of 63.548. And again, you can look at the periodic table that you might have in front of you, and it'll be very close to that number. Here's my work. If you don't like doing it the data table method, and instead you want to use the formula method, I've shown my work down here that you can follow. Okay? Either way will work. One is not necessarily more work or less work than the other. It's basically which one makes more sense to you. Alright, as promised, I told you I'd give you a little practice to do on here. This is not a real quiz. It's completely optional, and if you go to the end of the video, you can actually check all the answers. But give yourself a chance. Try this on your own. So I've made a table, and notice that I've used isotope notation. I have the name of an element, and I have an isotope. And I'm asking about how many protons, neutrons, electrons, and the mass number. And then you can fill in the missing blanks, A, B, C, D, E, F, G, H, I, and then check your answers with mine. And then finally, I gave you a average atomic mass calculation to do here, as well as a made-up question about extra credit that you really don't get extra credit about. What is a cation? To see if you're paying attention. All right, you want to go ahead and pause the video right now and work on that, and then when you're all done, I will click and you will see the answers to all these. If you have specific questions you couldn't get an answer, please let me know. I'm probably not going to go through the wording on all of those. I might spot check a few. All right, so as we go through that, the answers are shown up here. The first one should have been pretty straightforward. We know that the protons plus neutrons have to equal the mass number of 65, and this number is the mass number given in isotope notation. Second one should also be relatively easy. If argon has a mass of 40, it always has 18 protons because its atomic number is 18. Of course, you need a periodic table in front of you to answer this question. You can't just pick it out of thin air. And if it has 18 protons, it must have 22 neutrons to equal a mass of 40. And because it's a neutral atom, the number of protons, the number of electrons must be the same. On the barium ion, that's a cation, you have here 56 protons. If you want it to have a 2+ charge, you want to have 54 negative electrons. 54 negative and 56 positive get you the 2+ charge. Now, if we're just assuming that it weighs 137 based on the periodic table, that's the closest number to the barium atom. Remember, electrons don't have a mass, so that's not going to change the mass. And once we commit to the 137, and we know we have 56 protons, then you must have 81 neutrons. As for the average atomic mass, if you set this up correctly, there's 3 isotopes. I've given you 2. You have to add the third one in. You should get out an answer. If we round it to 5 sig figs, 119.79. And finally, the extra credit, a cation is a positively charged atom, or an atom that has lost an electron. I hope that was helpful for you. Thanks for paying attention. Thanks for trying this. Good luck with all your studies in chemistry, and take care. Bye-bye.